Hello, welcome to the second video on how you would go about doing the Core 3 coursework and the numerical solution of equations. Um, Now what this coursework is all about is we're going to be solving equations. We're going to be solving equations which we do not have an analytical way in which to solve them. By that I mean, let's take for example the equation, let's just insert an equation in here. Um, X squared plus 5x plus 4 is equal to 0. Now this is a quadratic, and by factorising, it's quite easy to show that we can factorise this to get x plus 4 multiplied by x plus 1 is equal to 0. So our solutions to this equation are going to be that x is equal to minus 4 or x is equal to minus 1. We have solved the equation analytically there. Now what I mean by analytically is that we have solved it and they are the exact values. Okay, we have used logic, we have used our rules of algebra to be able to manipulate this quadratic, factorize it, and then get to a couple of solutions. The quadratic is nice because actually, even if we couldn't factorize that, we can still use the formula. We could still use completing the square. Any quadratic can be solved analytically to find the exact solutions. We're not going to get any approximations with the solutions. The solutions are going to be exact. Now, you could also have, if we look at cubic, I'm just going to type in cubic equations, and there we go. So there we go. On Wikipedia. Hopefully this will work it out. Now a cubic equation also has a general formula. The trouble is it's an absolute nightmare, and you can see here it becomes quite tricky. I'm trying to find the actual formula for it. There is a formula for it, but I can't quite see it on here. It's a very big formula, and it's actually not often very useful to do. I mean, you can see here it's quite a reduction to a depressed cubic. I never knew cubics could be depressed, but we've got a problem basically when the power, the equation, is higher than 2. With cubics, we could do a bit of trial and error. We did that in Core 1, where we did trial and error. We looked at the factors of the constant, substituted in to try and find a factor. And in general, we can do that to any equation, but often that doesn't quite work. In fact, there's a formula for a cubic. There's a formula for a quartic. But for any formula, any equation where the power is greater than 4, there is no analytical solution. So, for example, if we take our analytical method to be able to get the solutions. So if we take this equation here, this is an example of a quintic equation because the highest power is 5. Now, we've got no way of solving this analytically in general. There are some quintics which you can solve analytically, but in general, we do not have the methods known to us at this stage where we can solve this equation analytically. So we've got to figure out a way in which we can approximate solutions to this using numerical methods. Now, the first method we're going to use is the change in sign method. And what I want to do is to show you the coursework criteria for this change in sign method. Okay, so this is the coursework criteria sheet, which you'll all be marked on. The first domain for 3 marks is the change of sign method. We're going to use the change of sign method to solve this equation. Now, for 1 mark, the method is applied successfully to find one root of an equation. Okay, let's see how you'd get that mark then. So, there's the equation. Our first step is we're going to just get a sketch of the graph to see. We're going to get a sketch of the graph. Let's just get this right. Y equals that. Okay, so with our dynamic GeoGebra package, it was 5x to the 5. So I can change this now to 5x. No, it was 1x to the 5. Sorry, apologies. So I can change that to 1x to the power of 5. b was 0 because there was no x to the 4s. There was no x squareds, x cubes. There was no x squared, so let's get that to 0. And there was an x which was minus 5. And let's just get this right, and it was plus 3 there. Okay. Now, we can see, now let's remember, the solutions to any equation are where the graph of that equation crosses the x-axis. Okay, so the solutions to this equation correspond to the roots, or the roots of this equation correspond to the roots of this function. Okay, the roots of this equation correspond to the roots of this function, and the roots of this function are where the graph of this function crosses the x-axis. So we can see here, in fact, you can intersect some points here. If I click on that one down there and go to intersect two objects, if I intersect that graph and click on the x-axis, we have 3 points A, B, and C. These are our roots. Now we can, if we look at the criteria, it says the method is applied successfully to find one root. We only have to find one root of this. Okay, so let's find root A. Why not? Okay, now we know it's between -2 and -1, but that's not enough information. We know it's probably between -1.5 and -2, but we still need more information. We want to get it more accurate than that. Now, what we should notice is, if we zoom in a bit, in fact, zooming in, we can see it's in between -1.5 and -2. If we take a point to the left, to the right even, of our root, point D, if we look at point D, and I can move that down, yeah, I've got another point E. I'll get rid of that. Right click, delete. Go to a point D, and I can move that along the graph. Let's just go to right click and go to object properties and show label value. Okay, you can see that the value of this, the value of the y coordinate, that's annoying, there we go. The y coordinate is positive. If I take value to the other side, to the left of it, and object properties, show label value, you can see that it's negative. The y coordinate is negative. Now what we've got here, because the root corresponds to a place where it crosses the x-axis, on one side of the root, the value of the function is going to be positive, and on the other side of the root, it's going to be negative. There's a change in sign whenever a root appears. Okay, there's a change in sign wherever a root appears. So this is why it's called the change in sign method, because we're going to be looking for a change in sign. Now, it's not enough for us to just use the graphing package to solve this, okay, because we're only as accurate as the graphing package. So what we're going to do is we're going to use Excel to be able to find this graph. Okay, so first of all, looking at the graph, we know it's between -1 and -2. So there's a value of x, Excel even, and I'm going to create a little table with x and f of x. Okay. So let's create my table. Now I know my graph, my root is in between -2 and -1. So I'm going to go -2, and I'm going to add, I'm going to put that plus 0.1, okay, to get -1.9, and then I can drag it all the way to -1. Okay, so we know from the graph that the root is between -2 and -1. So I'm going to search for all the values between -1 and -2. Now here, I'm going to substitute in our x value into that formula. Now our graph, let's just remind ourselves what the graph is. I'm going to copy and paste that into Excel. Oh, didn't mean to do that. Let's go copy and paste that down. We'll get an equation, right? This is our equation. So what we're doing is we're going to equal. Now I'm mega careful with brackets in Excel. It's that value to the power of 5. So that little hat thing, which you can get from the that little hat thing from the inverse, if you're shift 6 will get you that. Minus, now 5 multiplied by brackets. I'm really careful with the brackets here. In fact, I might just put that one there. And then do another set of brackets. I always put more brackets than what I need to, but I know that I'm not going to make a mistake. Okay? Plus 3. Okay, so there's the value of this function when x is minus 2. Now the beauty is we can just drag this. And now, I'll just make that look a little bit nicer. There we go. We look where f of x, there's a change of sign. Now it's negative, 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 positive. Brilliant. Here is our change of sign. Okay, here is our change of sign. And what we can say is that our x value now is in the interval, and how we would write this, we would do square brackets, it's in the interval between minus 1.7 and minus 1.6. Okay, that's where our solution lies. Okay, so this is what we call an iteration. After one iteration, we've managed to get x is minus 1.7, between minus 1.7 and minus 1.6. Now the trouble is, if we count the number of calculations we've done, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The number of calculations is 11. Okay, Excel has calculated 11 different values just to get the root in between those two values. Now this will become significant when we look at comparing methods afterwards. Okay, so now we're going to copy and paste this table because my formula is already there. We can be a bit lazy here, but this time I'm going to go between minus 1.7 and I'm going to go up in minus. I'm going to go up in, if I click equals, this time I'm going to go up in 0.01s, and I'm going to go up to minus 1.6. Okay, and I'm going to clear that because I don't know, so fill, no fill. Okay, we're going to search between minus 1 and minus 1.6 where the change of sign is. Now the change of sign is there, negative, positive. Okay, so we've increased our accuracy to our root even further. Okay, so let's highlight that. So now we can say that x is in the interval between minus 1.62 and minus 1.61. Effectively, this is a trial and error. It really is a trial and error. And so number of calculations, again, which Excel does, is another 11. Now imagine if you were doing this by hand. This would take you ages. Excel is a fantastic machine to do this. Okay, I'm going to do it again. Okay, this time I'm going to go between minus 1.62 and I'm going to add 0.01 to it. Okay, brilliant. Let's get, that might not be where the change of sign is. So now it's between minus 1.62 and minus 1.61. Where's the change of sign now? Right, it's there. No, let's get that. There. Brilliant. Now, how far do we have to go? Now, we want it to find the answer to 5 significant figures, okay? So, we're not quite there yet. Let's do another one. Okay, this time it's going to be between minus 1.619, and this time we're going to add there. So that's a bit annoying. They're all going to go yellow, but there we go. It's just no fill. No fill. Right, where's the change in sign? Now change in sign is there. Okay, so once you get the equation set up, this is very, very easy, okay? Let's do another one because we're not quite there yet. Okay, so mine is between minus 1.6181 now, and this time we're going to go up in even smaller steps. Okay, so between minus 1.6181 and between minus 1.618. Let's get rid of that, because we don't know where the change of sign is. The change in sign is there. Okay, so we're going to highlight those ones. Okay, just move this over here. And we're going to keep going because we haven't got quite got it to 5 significant figures yet. Okay, so minus 1 point, well, it's minus 1.61804, and we're going up in another even smaller steps. Look how easy this is with Excel. Right, we're getting really tiny numbers there. That e to the minus 7 represents a really tiny number. We're getting closer and closer to this little ripper, which I am happy with. The change of sign, well, there's minus, there's positive, so the change of sign is in there. Okay, and just do one more to be safe. And in the extent they want in the coursework, they want you to have them to a certain amount of significant figures. Okay, now what's happened here actually is that we need to put them there. So I had to move those columns a bit so we could get all of it. Excel doesn't always get it all between. So let's just minus 1 point. In fact, no, we've done it. Okay. Oh, here we go. Excel's going mental. Right, let's just clear all that. Right, we've done it. Now, let's just examine why we have done it. We've got it accuracy down to 5 significant figures. Now, we could go on forever and ever, and it's never going to be 100% accurate. Okay, but what we've got it, okay, if you look here, both of these values, we know the root is in between minus 1.618034 and minus 1.618033. Okay, now if we look, both of these values, okay, let's just highlight them, and I'm going to put them there. It's because it isn't based on another formula. If I copy, right click, paste special, and go just paste the values, that isn't going to ignore the formulas. Okay, now if we round this, if we round both of these, and if you go to equals round, and we want it to 5 significant figures, okay, and I drag, we get exactly the same answer. Okay, so we have solved our equation. Okay, the solution to our equation is minus 1.61803. So one of the solutions, you have to be careful there. One of the solutions is x is minus 1.61803, but we have to say to 5 significant figures. Okay, because we could go on and on. We're never going to get this 100% accurate. We could go on and on, but we've solved one of the equations, the equation for one of the roots, and we've got it to 5 significant figures. Okay, so let's see how that compares to the mark scheme. So the method is applied successfully to find one root of an equation. Brilliant. We've done that. We've done that. What you're going to do is in your Word document and in your report, you're going to have screenshots of the graph, and you're also going to insert these tables in, all of them. Now let's just count how many calculations we did there. We did 11, 22, 33, 44, 55, 66. Number of calculations was 66. Now, if you're doing that by hand, that would be quite a lot of calculations. Okay. How many iterations have you done? Well, we did it once, twice, thrice, 4 times, 5 times, 6 times. Okay. So we did 66 calculations with 6 iterations. Okay. These are going to be useful for when we compare the other 2 methods in terms of speed and number of calculations which you have to do. Okay. Now, we also need to create, because if we look at what it says there, error bounds are stated and the method is illustrated graphically. Now, where it says illustrated graphically, it means you need to explain the method using this graph in your report. Okay, where it means error bounds, well, our solution is minus 1.61803 to 5 decimal places. Now, what that means is our error bounds are going to be like this. How we'd write our error bounds, we'd have to plus or minus, because basically it's this. It could be plus or minus. Now that we've got 5 decimal places there, so I'm going to go 0.12345 plus or minus, and then put a 5 there. It could go either way. Okay, this is what we mean by error bounds, putting a plus or minus 0.000005. Basically, the solution can't be bigger than minus 1.6180200. Let's get this right. The solution can't be bigger than minus 1.618025, and it can't be, it can't be smaller than that. No, it can't be bigger than that, and it can't be smaller than minus 1.618035, because if it was smaller than that, then it would round to a 4, and if it was smaller than this, then it would round to a 2. Okay, so error bounds, that's an important part of getting the mark. You need to do that. Okay, so we've solved our equation for one root to 5 significant figures. We've worked out how many calculations it took, how many iterations it took, and we've stated the error bounds. Now, the final part, it says there, an example is given of an equation where one of the roots cannot be found by the chosen method. There is an illustrated explanation of why this is the case. Now, if we get rid of all, these points A, B, C, D, and E, there we go. Now, this is where we need to play, okay? We need to get an example. Now, look there, that's a perfect example there. Right. We need to get an example where we don't find the roots. Now, look at this one here. This root here, there's 2 roots. Now, from up here, if we don't zoom in, it looks as if there's a root. Well, it does look, maybe there's 2 roots, but the 2 roots are really close together. Okay, they're really, really close together. Now, looking at the graph from above, we would say that the solution was between 0 and 1. So let's do the change in sign for this one here. Now, what is it? 3.1x to the 5 minus 5x plus 3. Perfect, because if I just clear all of this stuff now, we know it's between 0 this time and 1. Okay, let's get rid of that. All that. We know it's between 0 and 1. This time, we've got to multiply that by 3.1. So if you keep all of this up in your Excel stuff, you'd have less work to do. So this is the new function which we're trying to do. Now, you can see clearly from the graph, there's a couple of roots there, because the roots are really close together. You can see that they're really close together. But the trouble is, when we do a change of sign method between 0 and 1 with the function which I just found, you can see here there's no change of sign. The method has failed. So what you're going to have to do for that final mark is find an example like this where the roots are really close together, explain it graphically, get a picture of the graph on you can always print screen, and then show using Excel that there is no change of sign, even though there's some roots there. That is how you would demonstrate failure in this case. Okay, so that's the change in sign method, and I hope that's explained that well. Next video will be on the iteration method.